Okay, so we're going to take a look at chapter 11, which is electricity. Okay. All right, so when we're talking about electricity, what do I want you to focus on for the exam? Okay. Sorry? Yeah, we'll do all that. Okay, so first things first, we looked at what is a series circuit and a parallel circuit. Okay, series circuit, as we said, was something where there was only one route or one path. Okay. So there was only one path to your charge traveling through the circuit. One path. So this is known as series circuit. If anywhere during the circuit, if your circuit breaks down or the bulb goes out or whatever, then of course your circuit breaks apart and stops working. In a parallel circuit, you have more than one path, so the electrons have more than one route to take by. Okay, and so even if one of the light bulbs goes out, your circuit can still keep on working. Okay, that's the difference between a series circuit and a parallel circuit. Okay, so when we're talking about our rules and regulations in regards to series and parallel, we're going to start out with looking at your KVL, KCL, which is Kirchhoff's voltage law. Okay, and this is Kirchhoff's current law. Okay, and of course you have Ohm's law, which is for resistance. Okay, Ohm's law for resistance. So we will start out with our original, which is V equals to I times R. V stands for your voltage, I is your current, and R, of course, is your resistance. Okay, voltage, current, and resistance. In terms of our circuits, in a series circuit, your current stays the same. So I total current, stays the same all throughout the circuit. Okay, your voltage, on the other hand, is added, so V1 plus V2 plus V3, and so on and so forth. Your resistance as well is added to R1 plus R2 plus R3, and so on and so forth. In a parallel circuit, okay, your I is the opposite of what it was in a series circuit. So the I's are added. And your voltage stays the same. The voltage stays the same in a parallel circuit. And your resistance is 1 over R total, which equals to 1 over R1 plus 1 over R2 plus 1 over R3, and so on and so forth. Okay, so these are some of the rules and regulations in regards to how we solve for circuits. A few other things of note that we need to remember are as follows. I, current, measured in amps, is Q divided by T. Q, of course, is your charge, measured in coulombs, and T is your time, measured in seconds. This is coulombs over seconds. And Q is also calculated using this formula, which is the number of electrons or charge times the charge of an electron, which is 1.6 times 10 to the negative 19 coulomb. So this is the charge of an electron. Okay. No, this is it's 1.6 times 10 to the negative 19. This is the correct one. Okay, that might be a mistake. Okay. in terms of other things that we need to remember from this chapter is I want to do maybe a question where we take a look at a circuit and how to solve for that circuit. Okay, and let's do something like so. So let's take, we're going to erase this. This is from the Nelson Physics textbook, the new version of it, page 535. And this is question number, let us see, question number 4. Question number 4. And question number 4 looks like this. It's got okay. So this is what my circuit looks like. And what we're going to do is we're going to try to solve it. So we'll start out with my easiest load resistor right here, which is 5.5, and we're looking for R3. So R3, which equals to V3 divided by I3, which is 5 divided by 0.5. And what do you get? So this is 10 ohms. So that's our first starting point right here. Okay. Now, in terms of circuit, this is a series circuit, but it has a couple of parallel sections to it. So if this is 2.5 volts right here, this is also 2.5 volts because both of those are parallel to each other. Correct? So if this is 2.5, then R2 is going to be 2.5 divided by 0.3, which is what? So this is 8.3 ohms right here. Okay. Now, this is a series circuit. So if this is 0.5 amps, that means right here is also 0.5 amps. If this is 0.3 amps, then right here this has to be 0.2 amps. 0.2 plus 0.3 gives you 0.5 because in a parallel circuit your current is added together. So this will become 2.5 divided by 0.2, which is R1. How much? So this is 12.5 ohms. Okay, now V4 is going to be 0.1 times 70, which is, so V4 is going to be 7 volts. 7 volts. Okay, now you're thinking, what's V5 going to be? Well, if this is 7 volts, that means this has to be 7 volts as well. If this is 0.1 amps, this has to be 0.4 amps, because 0.4 plus 0.1 gives you 0.5 amps. Okay, all right, and R5 of course is going to be 7 divided by 0.4, so this is 17.5 ohms right here. 17.5 ohms right there. Okay, now the total voltage of course is going to be 2.5 plus 5, which is 7.5, plus 7, which is 14.5. So this is 14.5 volts. And your R total is 14.5 divided by 0.5, which is, so this is RT, 29 ohms. And this is how you would do your circuit. Okay, done. Any questions? Yes, I know Aiden, of course our genius, has different ways of doing that same question. So if you want to learn his method, talk to Aiden. Well, yeah, next year they can find out who Aiden is too. He'll be in grade 12. Okay, so one thing that we've forgotten to talk about, of course, is electrical power. Take care. So this is change in energy divided by time. Okay, also known as work divided by time. Okay, two different formulas that we have right here. When we are talking about how much it costs, for example, to calculate electricity, of course, we know power is measured in watts. Okay, now you learned this in chapter 5, I believe, but we're looking at it in terms of electrical power. And when we're calculating the cost of something, for example, then we would write down in terms of energy, which equals to P times T. And then we talk about it in terms of we talk about this right here in kilowatt hours. Kilowatt hours. Okay. So for example, if I want to calculate the cost of using an appliance, I might do energy, which equals to cost times power. Okay, so the last thing that we're going to talk about here is electromagnetism, and this is chapter 12. Okay. Okay. And electromagnetism, we're just looking at in terms of how does electricity affect magnetism? How does electricity affect magnetism? And we talked about the 3 right-hand rule. So we're going to talk about conventional current and electron flow. Okay. If we're talking about negatively charged particles, we're going to use the left-hand rule. If we're going to talk about conventional current or positively charged particles, then we're going to use the right-hand rule. Okay. Now, what is the right-hand rule? We'll start with first one, which is a conductor. So this is a straight conductor. Now, this discovery was made by Hans Christian Ørsted, who said that if I have a straight conductor, of course without any insulation on it, and I want to figure out where the magnetic field will be around this conductor, then I would hold this conductor or pretend to hold it in my right hand. My thumb will point in the direction of the current I, and my fingers will curl around the conductor in the direction of the field. Which we called B, magnetic field going around this conductor. So this is the first right-hand rule. Okay. The second right-hand rule says if I was to take this conductor and coil it around, and this is known as a solenoid or a coil, and again, if I was to hold it in my right hand, then my thumb would point in the direction of, so thumb in the direction of the magnetic field B, and my fingers would be curling up in the direction of the current. That's the second right-hand rule. Okay, so far so good. Now, of course, I'll have to erase some of this stuff to show the third right-hand rule. Now, the third right-hand rule says if I have an outside magnetic field, okay, so outside magnetic field where I have a magnet like so, and my field lines, of course, going from the north to the south. Okay, that's an outside magnetic field. Now I take a conductor, a straight conductor, and I put it through this magnetic field. And of course I turn on the electricity. So this conductor will have its own magnetic field. So I have an outside magnetic field, which is a B right here. And then you have this magnetic field, which is B right there. Of course, if I take my open palm, my fingers would be pointing from the north to the south. So this is your wrist right here. This would be the edge of your fingers, edge. Okay. So of course I take my wire, it has its own magnetic field, and the two create an